Another example of doing this thing where you make electrons live in very narrow energy range was a surprising discovery that happened in the late 80s and early 90s, which was a class of materials. I told you about superconductors. I told you when you go get your MRI, your machine is cooled with liquid helium. The class of superconductors can superconduct at relatively high temperatures. Temperatures, I mean liquid nitrogen, and some even larger than that. Again, exhibit this same some of the same phenomena that I described to you. Of course, being able to get superconductivity without having to pay a lot to cool something down has a lot of advantages. These superconductors are also quite, they can make very, very strong magnets. So this is a fun example of a sumo wrestler being levitated. But more importantly, these superconductors are being used in a lot of different applications. For example, power transmission. Actually, there are actually pilot studies where if you want to transmit a lot of power to a certain region, which is very, for example, populated, actually having a superconducting wire made out of these materials with these electrons interacting very strongly with one another actually allows you to pass a lot of power with a very less number of wires in terms of like normal wire, like copper wires that we use. If you have also been following the news, there's been also a lot of investment in new kind of ideas for fusion. Fusion is one of those things that people try to create by, power of the sun on the planet. Actually, that requires large magnetic fields. And there are a number of companies that are actually using these high temperature superconductors to create very strong magnets used for this fusion application. All of this said, we have no idea, well, we have some idea, but we don't actually understand these materials, how these superconductors work. We don't understand how they become superconducting, why they become superconducting at such high temperatures. If we understood that, maybe we can improve the situation even further. The reason we aren't able to understand it is because electrons in these materials, because there are many of them living in this very narrow energy range, they have basically very highly entangled states, which we simply cannot compute using our current theoretical and computing ability with our classical computer. In fact, one of the motivations building a quantum computer is actually being able to solve these problems, is being able to simulate these interaction of many electrons in order to understand problems as hard as this, and also related problems in biology and in chemistry. Okay. Now, in the next 15 minutes, I want to now switch gears and tell you about an example of electrons interacting very strongly with one another, and a puzzle that's been around for a long time about electrons interacting. I told you about metals being liquid-like, moving. I told you about superconductors, electrons pairing up and creating this unusual state where they can flow without resistance. I want to tell you about a state that happens is proposed to happen in a lot of situations in which electrons actually make a kind of crystal. This crystal is created by just electrons repelling one another. I don't mean a crystal made out of atoms. I mean a situation in which electrons kind of repel one another the way they arrange themselves to a lattice. As I'll show you, this is an example which has connections actually to many of these problems that we don't understand, because this is perhaps the oldest problem in which electrons interact with one another. Where did this problem come from? Well, this problem was actually considered back in the 1930s by someone who taught at Princeton, Eugene Wigner. And he basically considered a situation where electrons repel one another and electrons can just make a crystal. And this was the first example of a collective state of electron in which they're interacting. And people have been looking for this for a very long time. Now, a little bit about Wigner. So actually, when he wrote this paper at Princeton, he was a refugee. He came from, he was born in Hungary. He was taught at Berlin, and he basically escaped the Nazis, immigrated to the US. Incidentally, Princeton hired him, and then they fired him. And then they realized they made a mistake. They rehired him. Actually, if you read his memoir, he has an interesting proposal about idea about why he was sort of let go. Is because he hired two people at the same time. One was him, and the other one by the name of John von Neumann. He's a kind of a sort of a father of computing, father of many things, and his thinking was maybe they were more impressed with him than me. But if you read his memoir, he's such a modest man. He had, of course, enormous contributions to physics. He got the Nobel Prize, but you might not know that he was actually one of the key people who convinced Albert Einstein to write a letter to President Roosevelt about the possibility that we could build an atomic weapon, and we should build one because the Nazis may build one, and he worked on the Manhattan Project. So here's an old problem that Wigner proposed. So how do we go about looking for this crystal? Well, let me bring you also to the sort of the area of some modern material and modern ways of imaging electrons in material. This is what I do for a living. I try to visualize what electrons are doing in all these complex materials that I told you about. And the instrument that I use is one which relies on a phenomena called quantum tunneling. It's not a microscope, it's one that you look inside, like with light. This is a microscope in which we bring a very sharp tip, metallic tip, close to the sample surface, and you're not actually touching the surface. Okay? But there is something that happens quantum mechanically, which is an electron that is living inside, let's say, the tip, and actually quantum mechanically tunnel across to the other side into the sample. I'm going to solve, this is again, equations, a quantum mechanic equation that you can solve. You can launch an electron from this side, and you can come to the vacuum barrier. And of course, sometimes the electron will just turn around and not go anywhere. Actually, there's a finite probability that the electron can actually hop across this barrier and go to the other side. This probability is very sensitive to the distance between this sharp tip and the sample. And in the late 80s, this instrument was built for the first time to try to sense this quantum mechanical current between the tip and the sample. And when they raster this tip across the surface of a piece of silicon, they were able to, for the first time, image individual atoms. Because the probability of electron tunneling between the tip and the particular location depends on whether the atoms are there or not, or you're in between them. Okay? So I came into this field when people were using this instrument to do a lot of imaging of different atoms, different molecules, different structures of materials. It's a very powerful tool. The question for a few of us was, can we use this microscope to study these more interesting properties of electrons, these electron waves, these electrons being in a superconducting behavior, and so on. We're not interested on the atoms. We're actually interested in electrons moving around and their quantum mechanical behavior. Now, to do that, we had to, generation of instruments had to be developed, becoming better and better and better. And this is kind of one of our latest instruments at Princeton. It's so big, I just have to show you a drawing of it because, the picture doesn't show you that, we have to isolate it from the environment inside a bunker, float the room with a very heavy floor in order to make the vibrations so small, because this tip to the sample is shaking. It just sort of blurs out the picture you would get with this instrument. Yeah. Let's start nice and simple. A simple metal. I told you about electrons in a simple metal. They just look like particles. Here's a piece of copper. You use its instrument to image a piece of copper. It has a few defects on its surface. See the wave pattern, right? This is basically electrons whizzing around, and they make the standing waves that I told you about, okay? This is kind of like sanity check. using this microscope to actually see quantum waves. Okay, these are actually electrons behaving like waves. Okay? And you can study this, but this is kind of a very sort of starting point of applying this technology because we want to study more complex quantum states. So let's go back. So my lab uses this instrument to study many different phenomena. Let's go back to Mr. Wigner and his crystal. Okay? So what we want to do is try to see whether we can use this instrument to visualize not electrons being in a wave, but actually electrons making a crystal. Okay? And what we're going to do is we're going to use a new invention in materials, which is the isolation of a single carbon layer called graphene. And the reason we do that is that this material is structurally almost perfect. Carbon bond is so strong, it is very difficult to make an imperfection in this material. Of course, we can use, let me go back and I'll come forward. We can also use this instrument to image where the atoms are, where the crystal structure of this, the lattice of carbon atoms are. Makes this image where you can see, you know, everybody is sort of happily sitting and they're, so that you can find very, very large region of this material if you do the right procedure without any imperfection in the material. So what we learned from Mr. Wigner is that we want to get electrons to interact very strongly with one another to get to this state. So one idea is to just very few electrons. So there is, you know, it turns out that's one limit in which they interact very strongly with one another. Another idea is to actually apply a very large magnetic field. What does magnetic field do? Electrons are charged, and when you apply a magnetic field, it makes them go around in circles. When they go around in circles, what happens is that basically the probability for them to move around from one place to another becomes smaller and smaller. Okay. Remember, we talk about squeezing the range of energy where the electrons live to make them interact strongly. This is what the magnetic field does for you. Apply a very large field, it makes the electrons who live in a large range of energy, makes them live inside these very sharp, narrow regions of energy. Okay. So now we go and try to fill each one of these. So now we go try to look for what the electrons are doing. We're not interested in atoms. We want to look at slightly larger energy scale, a larger dimension space to look at, you know, when the electrons are moving around, what kind of behavior they have. Let me show you a little movie. So this is a movie of, basically with this microscope, we try to add the electron into the sample. See where the electrons goes in or where does it not like to go in. Let's just run the movie. Okay, this is the beauty of experimental physics. You just look at the data, and what I'm going to do this movie is, so this is a 300 nanometer, a nanometer is a billionth of a meter. We're not looking at the scale of an atom, we're looking at a larger scale. Pretty small scale, it's a third of a micrometer, okay? And you see a kind of bunch of jumbled things, okay? You see there's a little number here, and this number tells you that we have a way in which we can use an electric field to basically control how many electrons we have put into this region of the sample. Okay. So you look at this image, and what I'm going to do is I'm going to now increase the density of electrons. The number is just going to keep rising, increasing slowly with each frame. And you can sort of see that as we change the density of electrons, that we put more and more electrons, sort of a pattern emerges in this picture. Okay? Let me go to what the pattern is. So at the most ordered organization, you might have noticed in that movie, is that we have this arrangement of a hexagonal lattice to our observation. Okay? So what are we looking at? Okay? So zoom in. We have so what we have done in this experiment is we have this sheet, which is made out of a single thick carbon layer. We've added some electrons to it, applied the field to make them interact very strongly. We just came and see where we can sense where the electrons are in the sample. We see that there is this periodic pattern of features in this in this data.